Well, when we talk about the metaphysics of space, and we want to approach a space from a metaphysical perspective, then several questions are there to be tackled. So first of all, we can really try to answer the questions of whether space exists at all. So we can be sort of like realist about space or anti-realist about space. We can also would like to answer the questions of whether space is fundamental or it's emergent. But we also maybe would like to come up with a more concrete, intuitive, more specific model of space, so where more specific features about space are spelled out. And so we might want to be substantivalist about space and think that space is a real physical entity. And then we might want to be absolutist about space and think that space is a kind of absolute or fixed framework. Or we might want to be relationalist and think that space is just a set of spatial distance relations. We may also want to inquire whether space is a continuous entity or a discrete entity, and on the most fundamental constituents of space, whether space is really composed of points or maybe regions like gangs which are infinitely divisible, or maybe no, there are some fundamental building blocks of space that cannot be divided further, like atoms of space. And so in this talk, I really would like to focus on the debate between the continuous and the discrete model of space. And this kind of question is other questions in the metaphysics of space can actually be approached not only from a metaphysical perspective by inquiring into the metaphysical tenability of particular models of space, but also from an empirical perspective. And so really by looking into the physical theories and see whether they can give us an answer. So what I see really by looking into these two different approaches, I can see that probably the metaphysical approach to space really is centered on some alternative conceptions of space, maybe binary, or in any case, different alternatives of space, like continuous or discrete, point-like or atomic, and etc. And so from a metaphysical point of view, we really want to evaluate the pros and the cons, whether our models of space are metaphysically attainable or not, are adequate or inadequate, and etc. On the other hand, the more empirical approach really provides us with different ways, different models of space taken from different theories of space. So for instance, we can focus on Newtonian mechanics, we can focus on general relativity, we can focus on quantum gravity, and then they all give us different definitions of space. So in this talk, as I said, my approach is mainly metaphysical. However, I really would like to also considering some models of space, in particular the discrete model of space, which is offered by some physical theory, in this case, quantum gravity, which is really paradigmatic because it actually offers us an understanding of space, which is as a collection of chunks of space. So just to be fair from the very beginning, I have to say that, of course, that there are different interpretations of space within the quantum gravity, and so different interpretations of what these chunks of space might be. And so, for instance, Rovelli and Vidotto really endorse a discrete view of space, but they do not interpret these chunks of space offered by low quantum gravity as concrete entities. While other works, like by Vassallo and Esfeld, they really would like to take these chunks of space as concrete entities. So in my talk, I will be focusing on Vassallo and Esfeld's interpretation of the model of space in loop quantum gravity. And this is not because I think that Rovelli's interpretation is wrong and Vassallo and Esfeld's interpretation is right. It's just that from a metaphysical perspective, Vassallo and Esfeld's interpretation fits very well with the kind of debate we're having in the metaphysics of space. So when I first read the Vassallo and Esfeld paper on the metaphysics of space in loop quantum gravity, particularly they endorse a particular approach, which is a Bohmian approach, and we will see this later. Then I thought, well, the kind of reaction that a metaphysician of science might have after reading their paper is a surprise. Why? Well, because the metaphysicians of science really think the atomistic models of space are just metaphysical speculations, because we know that from general relativity that space-time is continuous. Also, we know as metaphysicians of science that we tend, by looking into metaphysical reasons, to evaluate discrete models as incoherent speculations. So we know that generally speaking, we might be favoring the continuous model over the discrete model of space. But of course, we have to really spell out this surprise in a more neat way. Then the surprise might have two different outcomes. So one outcome might be see, oh wow, Esfeld and Antonio Vassallo really gives us a discrete model of space, which comes from a Bohmian approach to loop quantum gravity. So discrete models are true. And this might be the reaction of very strong naturalistic metaphysician of science that really thinks that we have to go into the physics in order to know what is metaphysical, even conceivable or possible. Then we have an opposite reaction. It might be, well, look, Vassallo and Esfeld, we know from a metaphysical perspective that the discrete atomic models of space is incoherent, and so we cannot accept your interpretation. And this kind of reaction is normally typical of the armature metaphysics approach, that thinks that we can say what is physical and not physical appropriate interpretation just by sitting on our armchair. So of course, both are pretty naive reactions because, well, first of all, let's keep in mind that Vassallo and Esfeld offer an interpretation, okay? This is just an interpretation. As we saw before, Rovelli and Vidotto disagrees with this interpretation. Also, this interpretation on a closer look is metaphysically grounded because the reasons that they give to endorse this particular interpretation is metaphysically colored. So, of course, the metaphysical scrutiny is very much appreciated here. And even if it turns out that their metaphysical view is very well grounded and it's the right one, then it doesn't make it safe from a metaphysical point of view. We can still have conceptual questions, conceptual work to do. So if on the other hand, we really have this opposite kind of reaction, and so have the reaction of the armature metaphysician who think that he knows or she knows what the world looks like at a physical level, then my question would be, well, but are you sure that the discrete model offered by Vassallo and Esfeld is metaphysically incoherent? What are the reasons that metaphysicians give to support the view that discrete atomistic models of space are actually metaphysically incoherent? And are these reasons also holding true in the kind of discrete atomistic model of space that Vassallo and Esfeld presents in their work? So in this talk, I will assume that Vassallo Esfeld offers sustainable interpretation of low quantum gravity from a physical point of view. I do not want to engage here in which kind of interpretation is the best one for low quantum gravity, but what I really want to do is to investigate whether the low quantum discrete model of space is metaphysically incoherent. And I will conclude that actually it is coherent and it can really enriches our way of thinking discrete models. And so the discrete models can be metaphysically coherent. In particular, this one is coherent. So really the main goals and what I really would like to do during these 2 hours is really to bring a metaphysical and physical debates in touch, because I really like this. And then also on one hand, give new metaphysical tools to conceptualize the physical discrete models that we find in physics. And then on the other hand, to provide a metaphysics debate with new naturalistic discrete models of space, like the one that Antonio and Vassallo offer. And so in overall, really to show discrete models and to put them in a better light. So how I will proceed? Well, since I'm not very sure if all of you have a background in metaphysics, I will just introduce you with the metaphysical tools that I need for the rest of my talk. And then I will really go into the debate between continuous and discrete models of space. Of course, this is a huge debate. I cannot in 2 hours summarize all that, so I will just focus on a particular problem, the device argument. Then I will go into low quantum gravity, in particular on this model by Vassallo and Esfeld. And then I will try to appreciate this model from a metaphysical perspective and inquiry on how this bears on the more general debate. So let's get started. So here we will just be talking about substantivalism, continuous space, discrete space, and atomistic space. So what do we mean by substantivalism? Well, here I just put on the right side some collections of theses that all together really constitute a substantivalist view of space. And of course, I'm not saying that a substantivalist has to actually buy into all of them, but I think that they can really give a very complete picture of what substantivalism amounts to. So the first is really the awareness that the physical world consists of material objects and also of a physical entity called the space. Of course, space can also be as a kind of like container within which objects are located, but a container which is not contained by anything else, because space is not located with anything else. So suppose now that we have some cavities in the region, some tiers of space, then these cavities are not regions of space, but they are called holes in space. Space possesses some intrinsic nature of some kind, like material objects possess some intrinsic nature of some kinds. And also it possesses certain topological properties. For instance, in classical mechanics, we can say that might be a collection, manifolds of points that conform to the axioms of Euclidean geometry. We can also sometimes say within the substantivalist view that actually space constrains the motion and the dynamics of material objects. And lastly, we can also think of space as a kind of like word-making entity, in the sense that, well, when we say that objects that are located in the same space.
You take questions, short questions, or
clarificatory questions? Yes, go ahead. Yeah.
Yes.
Just super short. The physical world consists of material objects and space. Suppose I think the material world consists of space, the same as you mean, material objects and the electromagnetic field. Where do you place it?
Yeah, so you think, yes, I mean, it's definitely a substantivalist perspective. If you think that space is a kind of entities to which the electromagnetic properties attach to. So the electromagnetic properties, so you can see the electromagnetic field in 2 ways. Either some properties that are instantiated by points of space, or as a kind of independent physical entity. So if you think of the electromagnetic
physical entity, it's a material object. You would call it a material object?
Yeah, maybe I will call it material entity. Sorry. Yeah.
Okay. So the electromagnetic field, if it has independent degrees of freedom, it could be a material part of the material object.
Yes. So if you think of the electromagnetic field as an independent entity that has its own dynamics, for instance, and does not
compatible with both, are you saying? Both
yeah, in both the cases, if you think that space is a physical entity, that in both the cases you are a substantivalist. So it doesn't really matter how you understand the ontological status of the electromagnetic field.
Oh, it does, because you're separating material object and space, and the electromagnetic, it's in between. The gravitational field is in between, and so
yes, sorry, it's just because here I was not thinking.
I'm just asking, if I have modern physics and I have substantivalism, where do I place the electromagnetic field and where do I place gravitational field? Just give me one option. It's so I can follow. Otherwise, I'm lost because I'm outside my physics.
Okay, so you can think that either the electromagnetic field is a material object or that it's just a collection of properties of space. Yeah.
And the same for the gravitational field?
Yes.
Okay.
So for
two options.
any
yeah. Substantival. Okay, thank you.
Yes, you're welcome.
Thank you.
Good. So yeah, we can also think like in my last thesis that I was explaining, that space is a word-making entities in the sense that sometimes we say, well, as long as objects are located in the same space, then they are parts of the same physical world. Okay, so then we can think of space as this word-making entity. So what about a more specific models of space? So what about, first of all, the pointy continuous model of space? Well, they, the people supporting this, this model really think of space as a kind of like a gap-free. We don't have really, I would say like distances, but then I will explain it better. I mean, you can just think of space as being like smooth, as being infinitely or indefinitely divisible, and it can be regarded as with this fundamental entities called points, which are dimensionless and extensional points. And so really there is no limits on the number of points that space contains, and there is also no limits on how far we can divide really matter, because you will still find points and points and points. So normally this continuous view sees points as the kind of entities that constitute a space, and also matter can be infinitely divisible further and further. On the opposite view, we have a space, a discrete space. And here I defined a space as a discrete if and only if for every partition on a finite extended regions of space, we can partition space, and then we have a finite extended region of space. So we have this extended regions of space, and then we partition it into a countable number of regions of space. Okay, so in different kinds of regions, and then each of these regions is further composed of individuals, like the picture above, or countable sets of points. And then individuals and points are finite. Okay, so we have a finite set, finite number of elements, either individuals or points. Then what is the atomistic view of space? Well, it's really the same, but as the building blocks of our reality, we have atomic regions of space, where these atomic regions of space have a kind of individuality. So they are called individuals, and regions of space can be defined as atomic regions of space if and only if it has no proper parts. So it means that it's a kind of what we call in metaphysics is a mereological atom. So atomic regions of space, this kind of atomic regions of space, sometimes metaphysicians call just them atoms, okay? And in this talk, I will assume that atoms in these atomic regions are extended, so they have an extensions. Okay, so how we can describe the debate between the pointy continuous view and the discrete view, atomistic discrete view of space? Well, normally in metaphysics, we regard the point continuous view of space to be the standard, the orthodox view, as if it was really like the winner. And why is it so? Well, because we think that, well, general relativity told us that space is not discrete. But then there is a problem, because the pointy continuous view of space is vulnerable to a paradox, which we call the plurality paradox, and which comes from sort of like Zeno worries about the continuous space. And we will see it later. And so in front of this plurality paradox, then it seems that actually the discrete view can be a solution. And so it's a kind of the winner. But then the problem is that, well, as many metaphysicians, I think it doesn't touch with physics. There is no physical grounds to say that the metaphysics view, the metaphysical model of space is discrete. And also there is this insurmountable problem given by WEYL's argument that we will see now. Okay, so what is this paradox of plurality, which is really a problem for the pointing continuous view? Okay, so take a segment, okay? Take a segment in your continuum, okay, which is composed of an infinite number of point-like parts, okay? So then these point parts of this segment are either of zero length or of some non-zero length. If they are of non-zero length, then the total length of the segment will be infinite. But if they are zero length, then the total length of the segment will be zero. So in the pointy continuous model, as I described it before, then we know that 4 is the case. We know that actually points are dimensionless, extensionless. They have zero length. So we would end up with a segment with length 0. So, but this is not very intuitive, right? But then how can we say that this is wrong? I mean, it's not intuitively right, but it can be wrong, because given that an interval continuum of a continuum consists of points that are actually of zero size, then how can finite parts of this interval have length other than 0? So if we add nothing plus nothing plus nothing, we just have a nothing. So this is the paradox of plurality. So can the discrete view be an answer to that? Well, actually, yes, the discrete view can be an answer to the problem, because we have extended atoms of space with specific extensions, specific dimensions, specific length and size. But then the problem is that also this view, the discrete view, has been affected by a paradox, the WEYL paradox, which really puts the discrete view under threat. So what is this paradox? So WEYL was the first one who really put his argument really in the strongest form, and is called the WEYL type argument. So first of all, WEYL was probably biased by the thought that actually physics tells us that the metaphysics of space is continuous, because he says, so far the atomistic theory of space has always remained a mere speculation, has never achieved sufficient contact with reality. But then the problem seems to be more on the metric. Why? Well, he says, if a square is built up of miniature tiles, then there are as many tiles along the diagonal as there are along the side. Thus, the diagonal should be equal in length to the side. What does it mean? Well, here he's talking about the problem of the Pythagorean theorem, which is not recovered and it's not approximated if we have a discrete model of space. So let's look at these two boxes, these two squares on the left and the right. So let's start from the left. Well, we have A, B, and C. Let's try to think of the length of the segment from A to C, or in any case, the length from A to C. Then we have to count the numbers of atoms of space between A to C, which will be 4. The same is for the length from A to B will be 4. But now look at the length from B to C. Then we still have 4 atoms between B to C, okay? So, but this cannot be true because the Pythagorean theorem tells us that this cannot be true. So one way to solve the argument was a thought to think, well, if we have really very tiny regions of atoms, and then we really add more and more and more and more atoms, we subdivide the square where A is and B is, so every square of regions, every tile into more smaller tiles, then this problem will be solved. But no, these problems cannot be solved, as we see in the square on the right, because from A to B there are 8 tiles, from A to C 8, from B to C 8. So the argument normally goes like this for metaphysicians: if discrete space exists, it must approximate a Euclidean space. Then a discrete space does not approximate Euclidean space, and so the conclusion is that a discrete space does not exist. So we can even be stronger about this and say, well, if discrete models of space is metaphysically attainable, then it cannot be empirical. Well, given the argument above, then a discrete model is metaphysically attainable, so we should give up on empirical confirmation on the metaphysics of space. This, of course, would be the argument run by a metaphysician of science who supports the armature metaphysics view.
Vera, that argument
Yes.
only rules out a cubic discrete space. If you have another kind of discrete space, it's not ruled out by this argument. It's just a specific for one version of discreteness.
Yes. Yeah. We will see this later. Yeah.
Okay, sorry.
But can I ask one more thing? Sorry. Where is in this conclusion you have the notion of approximation? Where was the approximated? Where was the approximation in the previous example? There you were just concluding that because you cannot have the length of the diagonal exactly reproduced in this lattice, then this lattice structure was not tenable. If you just require, some approximation, then you have much more freedom to build up your lattice and to conclude its viability. And in fact, the same is if you choose non-square lattices. There are some geometries that you cannot reproduce with, I don't know, equilateral triangles in dimension higher than 2, but you can approximately reproduce them.
Yeah, so the thought here by metaphysician is that, well, I mean, with approximation is, okay, you can idealize and really approximate to, a kind of round number, but still you don't really get the result, the very same result that Pythagorean would get. But yeah, I understand that we need a more
I'm fine
specific...
if you rule out approximations to play any role. That it's fine. It's an argument. You can say, no, I want things to be exact. Otherwise, they're not metaphysically interesting. But then in the conclusion, in the next slide, you cannot use approximations in stating the conclusion.
I see. Okay. But yeah, so here I think so. So the argument is really, well, since the what we get does not approximate the results that we would get with the Pythagorean theorem, then really we have to rule out a discrete space.
I understand, but it's not true. Even with the square lattice, if the squares are super small.
Yeah, sure. It depends on it depends on your notion of approximation. Yeah, I am. Yeah. Good. So what's wrong in this debate? I mean, so we are kind of like now in oh, sorry, there is some more thing here. Okay, no, okay. So I got a message just saying one more. Okay, I will go on.
Yeah, the photo is for Schrödinger, it's not WEYL. The picture.
Okay.
Sorry, I just didn't want to.
Okay, sorry. I see. Oh, really? I see. Okay, so what's wrong? What's wrong here in this debate? So we kind of chose opposite views in this debate, but then we actually I think that both they are wrong, because the pointing continuous view is wrong, and then the discrete model view has a device argument, and so they what are they presupposing here? What are these two views presupposing? Well, they are presupposing how we can calculate length here. Okay, so we presuppose how we know how to sum or to count the length, and maybe there is something wrong with our assumptions, some assumptions that we can give up. So let's look more into how we really calculate length in the pointy continuous view by adding really in the sizes of the kind of points in the continuous view. Well, the plurality paradox really invites us to add up points in a line in the same way we add up 1 + 1 + 1 + 1. And so it really depends on the assumption that our ordinary conception of addition is for a non-enumerable infinitive of points. But then, I mean, are we really sure that we can adopt this kind of a way of counting length? I mean, this way of counting length actually would be grounded if the continuum behaved in the same way as ordinary finite quantities or the numerably infinite quantities. But here we have a non-denumerability. So according to this line of thought, which is implicit in the point continuous view here, well, if we have one segment and then another segment which is like 3 or 4 times longer, then we have actually exactly the same cardinality. So for the case of non-denumerable quantities, then probably length should not be based on number of points, on summing their size. What about in the discrete model of space? Can we give up our assumptions of how to measure length and how to calculate length in the discrete model? Well, here I focused on this paper by Chen, Intrinsic Local Distances, and solution to Weierstrass argument. And what is her conclusion is that actually, yes, I mean, we have good reasons to think that length should be counted like this in the atomistic view for 2 main principles that we have here. One is finite additivity. So for any natural number n and for any n-dimensional region x, if x is composed of finitely many disjoint regions y's, then the measure of x is the sum of the measures of y's. And this is applicable to our case in the atomic discrete model of space. We have also this principle size by counting. So assume that every atom has a unit size, then finite additivity entails that the measure of size of a region is equal to the number of atoms it contains. So it seems that we have some grounds to think that in the discrete model of space, we can actually endorse this way of counting the length by counting the atom. In particular, in this discrete view of space, we have different notions that really rely on sequence of atoms and also the number of atoms. For instance, we can define a path, like a path from atom A1 to atom AN as a sequence of atoms A1, AK, and N, such that for every K, AK and AK plus are adjacent, where adjacency in this kind of particular ties, as Carlo has just mentioned, it just means that it must be horizontal and vertical and diagonal adjacent, but then you can have a different kind of ties arrangement. And then the length of a path is equal to the number of atoms it contains. And then the path-dependent distance is that for any two atoms A and B, the distance between A and B is the length of the shortest path from A to B. So it seems that overall, like the metaphysical debate is kind of saying, well, the atomistic discrete view should count length by number of atoms, so the Weiss paradox applies, and so the standard view fares better than discrete atomistic view. But then, so I was really interested in going to the loop quantum gravity theory, which is the most prominent theory in quantum gravity that really gives us a kind of discrete analysis space, and to see whether there are some lessons that can be drawn from there for us metaphysicians. So here I will really give kind of philosophically usable descriptions of the theory. I'm not a physicist, so please interrupt me if I say anything wrong. So the loop quantum gravity is really this approach on canonical quantum gravity where we want to recast general relativity as a Hamiltonian theory. So we first of all want to reform. So also here, I know that there are two versions, the covariant and the canonical approach to loop quantum gravity. And here I will be focusing on the canonical one. So within this kind of approach, then we want to reformulate general relativity as really by interpreting the space-time as a 3+1 dimensional entity, where really these 3 dimensionals are spatial. So we have 3-dimensional spatial hypersurfaces, and then we have a 1-dimensional time. And then we want to proceed with the canonical quantization of the Hamiltonian general relativity. So the basic picture which I grasped is really like, well, first to find the Hamiltonian of the theory. The Hamiltonian is nothing the linear combination of class constraint. And then really what you have to do is to solve these constraints. And these constraints are the Gauss gauge constraints, the vector diffeomorphism constraint, and the scalar constraint, also called the Hamiltonian constraint. So normally in GR, we describe the space-time as a kind, as with M and G, with M is the manifold and G is really the metric field. And here we want to quantize a G. We kind of keep the manifold for now, for the very first step as it is, okay? Then I'm not familiar with the mathematical language, but for all of you who are familiar with the mathematical language, then what is important here is that a certain stage, the fathers of loop quantum gravity really decided to go for the Ashtekar variables, which are real SU connections. So they use the language of connections, and then also as a kind of other variable, real momentum field, which also in general relativity, they call it already an electric field. And then from then they kind of construct an holonomy and its conjugate flux variables to construct the theory. So this big intuitive picture that I have, and I hope it's right, is that really when we want to really quantize the theory, we need to find a Hilbert space, first of all, which kind of corresponds, which represents the physical states of the theory. And then in order to find this physical Hilbert space, we need to implement the constraint. So we have first this general Hilbert space with lots of degrees of freedom, with states that can be even equivalent, and then we kind of constrain the space more and more. So first we implement the gauge constraints, then the diffeomorphism, then the Hamiltonian, and so on and so forth, okay? And then of course this is not enough, because we also want properties, so we need operators like we have in quantum mechanics, okay? And so we need to define those operators. And the intuition was that, well, maybe some Wilson loop operators are well defined in the Hilbert space, and so we can extend this kind of idea of Wilson loop operators into other kinds of operators which are similar, or a kind of generalization from the Wilson loops of operators. And so that we can work within this framework, okay? And then really in the quantum states, what we have as really like states of the system, the quantum states of the system for quantum gravity, we have some kind of like a Schrodinger wave functional, okay? The same way we have in standard quantum mechanics. So let me first focus on the Gauss constraint. Well, it requires the physical system to be invariant under an internal gauge transformation. And in order to do this, what the fathers of loop quantum gravity did was really to have this intuition of identify a graph of links, lines, and nodes, points embedded in this mathematical manifold M, but stripped with geometrical structure. So what they did was then to color the edges and the nodes of the graph in terms of the SU2 irreducible representation, and then of the SU2 intertwiners. So let's think of this as quantum numbers, okay, intertwiners as quantum numbers. And so then these pit networks are kind of graphs associated with the quantum geometry. So here we have a picture. So this is a kind of like embedded spin network. Okay, so the spin network is still embedded in the manifold. Okay, and then we have these links, and then we have these nodes. So the nodes are these points, so the links are this line. And these spin networks embedded in the manifold, they form a basis of the Hilbert space, okay, of gauge invariant functionals. So normally we write down the spin networks as gamma is our spin networks, and then J, which gives us really the information of the links, okay? And so they are associated to an irreducible representation, SU2 representation. And then we have IM, which are really gives us the information of the nodes, okay? So the quantum numbers, the nodes. And we will see how this plays a very important role for the geometrical idea of the picture. Then we have the diffeomorphism constraints, okay? So the diffeomorphism constraints requires that our physical states are invariant under manipulation and stretching and shifting. What does it mean? That we can take our spin networks, we can stretch it, we can put it in another place in our we can put it in another place and still they are invariant, okay? This means that, well, before we had embedded spin network, but now we should not have embedded spin network. So we have to tie our spin network to equivalent classes of spin network under diffeomorphism. So here we really have to do this process of disembedding our spin network. And so we construct several equivalent classes of diffeomorphically related states and map each of them to a single state, which we call S-naught or abstract spin network state. What about the observable? So here I will be talking about the area and the volume observable. And so actually what we have been building so far is like spin networks, SNO states, but these are really giving us the eigenvectors of the area and volume observable.
Sorry,
So
just one comment. Yeah, just
yes.
one comment, if I can. On the previous part. So you're absolutely right, of course, about the S-naughts, but just to clarify, the S-naughts, so the equivalence classes of spin networks, it's true that they are not embedded in the sense that they don't correspond to any specific embedding, but also they should be distinguished from what are also used in loop quantum gravity in different contexts, like abstract graphs to which you assign the labels, because the equivalence classes of spin networks, the S-naughts, originated, as you said, by imposing Diffeomorphism invariance, they still carry information about the continuum embedding in two cases, either if the initial manifold was topologically non-trivial. So you could have, the graph wrapping around the hole. And then, of course, you could, remove any embedding, but you still add information around the wrapping number.
I see.
So it knows about the topology of the manifold. That's one. The second type of data you still have is that the link could form a knot with itself, for example. And that, of course, cannot be embedded in any precise location. That is not an invariant quantity, but you still know if the link has a knot or not. Sorry, not without the...
Okay.
An abstract graph will just not carry this type of information.
I see.
It's still not an abstract graph. It knows about the continuum nature of the theory.
Okay, yeah, thank you, Daniele. Thanks. Yeah, okay, good. Yeah. So here what we have to take out from this slide is that the area operator depends on the number of links which cross the surface. So when you see like a link which across the surface, then this link will generate a kind of area, okay? And then for the volume operator, well, the volume depends on the nodes. So on the quantum number, the intertwiners that is attached to the node, okay? And then really these observable areas and values produce eigenvalues which approximate the Riemann area and volume. And so when they do so, then the spin networks that satisfy these are called wave states. So here I really want to really focus more on the discreteness and on this intuitive picture, because it's really what I can grasp, and I really want to work more on this kind of intuitive picture. So the first thing is that when we talk about operators, actually they still depend on the structure of the manifold. So you see now here, they are still on sigma. So this means that they're not really Dirac observables, okay? So we can't really be satisfied completely with them, okay? And then they are discrete because, of course, like the spectrum of these operators is discrete, and because, of course, like the quantum numbers we attach to the spin and to the volumes are integer values. And so if we modify the spin networks, we kind of add discrete units or area, etc. So think of this picture, right? So we have an area operator, okay, we have a volume operator, and here, I don't know if you see but you can really see that around the node, there is some kind of volume, and then here the links persist through a kind of surface by generating area. So this, for instance, is a portion of a spin graph, okay? And we can really take seriously this dual picture that starts, okay? So the dual picture here, so for instance, we have this node, and then this region R is the dual of the node N, and then next to this region R, we have two other adjacency regions, okay? And then each link has this kind of dual surface. And but I've been embarrassingly silent on the length operator. this, I'm sorry, but it's because even though I read papers on the length operator, is still very difficult for me. But in any case, what I think is important to understand here is that if we take this dual picture seriously, okay, then you can see this curve gamma, and then we really think that maybe the length operator can have something to do with this curve gamma, can measure this length gamma, okay? And so really this length operator, hopefully approximately, it's a counterpart in general relativity spacetime, and really has also something to do with the links, because of course this kind of length operator measure this length of the curve, which is given in terms of the graph, and it's kind of like a dual to this surface here, which is painted by these two links. I don't know what my arrow is. These are two links by which are originated by N here. So we can say that the regions and the surface are defined on an S node, and that, so here we have this also picture taken from Rovelli's, and that really this set of black nodes define a region of space, and that the set of these black links really define the surface of this region. So here it's also a kind of like very simplistic but very powerful, intuitive picture where you can see that each link generates a surface, and then each node is a kind of volume, and we have different shapes here. So this is a warning that is found in Rovelli and Vidotto in 2015 in their manual on covariant loop quantum gravity, but I think it's of course applicable here. So they say, well, look, this quanta of space that we see, these chunks of space, which are just, given by the quantized volume, which associate by the nodes surrounded by a quantized area, then it should not be thought of as a quanta moving in space. No, because of course these are space, so we can't say that they are in space. So this is also a typical claim within the substantivalist view of space. Space is a container, it's not containing anything else. So here, if we have a tiers, of course we don't really have regions of space. So here, like chunks of space compose a space, are not in space, okay? And then Rovelli and Vidotto really urges the reader to interpret them as modes of interaction, okay? They also endorse the view that, well, this picture gives us some kind of non-separability or non-locality, because in the end of the day, the final quantum loop quantum gravity state is actually given by the linear superposition of spin networks of state, and then space is a kind of quantum superposition of wave state. So we have the same kind of conceptual problem or conceptual feature that we have in normal quantum mechanics. We have superposition, okay? And then we have also a problem of multi-mapping, because this kind of chunks of space are actually, of course, mapped to events in space-time, right? But adjacent chunks cannot always be mapped to adjacent events in space-time. Sometimes they are mapped to very distant events in space-time. And this kind of picture is not really liked by the primitive ontology approach. For instance, the one supported by Esfeld and Vincent Lam and Antonio Vassallo, who really hopes that we can have a clear ontology, okay? A clear picture of our ontology is, which consists of building blocks of our reality. So we have physical entity, a physical ontology, and from which we can build up our reality. And they said, well, look, we should not really read off the ontology of the form. We should not really conclude what our ontology is by reading off the formalism. We know that our ontology has to be discrete because the tradition of atomism, and we can build up our own ontology by taking loop quantum gravity with this kind of Bohmian approach, but with Bohmian, I more understand this primitive ontology approach, and really try to come up with an ontology that respects our metaphysical presuppositions of what an ontology should be. So we have to distinguish the kind of elements in the theory that really represent physical reality from the elements that are just a mathematical representation, okay? So I just want to explain this better because it's important. So the arguments that they give to endorse this interpretation are mainly philosophical, okay? So they stem from this atomism in Western thought, and I would add probably also this atomism of space may be coming from the metaphysical debates on the models of space, okay? So they are not really grounded on a particular physical reasons of what loop quantum gravity tells us about the world. So we have these chunks of space that we saw before as concrete atoms of space. They are related by continuity.
Can I make a comment?
Yes. Yes.
If you go back to the previous slide, you know that chemistry would, and the whole atomic theory would never be found if people had applied this methodology all the time, because it's tremendously successful because people decided that what the correct ontology of the world should be what works, not what we were used to.
Yeah. So maybe we can.
I'm not sure that historically one would claim much success for this methodology.
Yeah. I'm very interested in this, and yeah, maybe we can I will bring it up in the Q&A answer because yeah, I have a lot to say. So yeah, thanks. Thank you. Okay. And then, so they really endorse this contiguity relations, which is kind of like adjacency relations that we were saying before. And then they say that given a set X of n atoms, so that we can define an approximation function that really targets the most function. So we can still have a kind of connection between this discrete atomistic view of space to the continuous one. So what is really their metaphysical view here? So they still have the substantivalism about space. So we have chunks of space here. We have still adjacency relation. We have adjacency relations between contiguous chunks of space. But this contiguous relations is given by whether these chunks of space are connected through links and whether they share surfaces. We still have this atomic discreteness. We still have this arrangement of atoms of space. But then what about the WEYL argument? I mean, was not really applying? Well, we were saying before, if a discrete space exists, does not approximate to Euclidean space, discrete space does not approximate, well, discrete space does not exist. Well, here there is a lot to say. What were the assumptions or the WEYL paradox? Well, the Pythagorean theorem that the distance is calculated by counting of atoms, but also on the uniform and distributions of atoms, which had the very same shape, which had exactly the very same side, and they were arranged in a very certain way. So here, this is why I really entitle my talk Space of the Many Substances, because I really like about this model is really the variety and multiformity of space at the fundamental level. So we don't really have one shape, one size atoms of space, but several chunks of different shapes, different forms. And then length, the operator length, I would like to hear more about this operator length in the Q&A answer, but apparently it's really not associated to the number of atoms. Of course, it's more associated to links, number of links. And so, of course, we might also think, as I mean, all the people working in loop quantum gravity are showing that, of course, it's a working hypothesis and defensible and feasible hypothesis that discrete kind of model approximate to continuous models. And if it's so, then we would not have problem with the Pythagorean theorem. So we don't have to presuppose that atoms are arranged like this. Then a more kind of interesting question for me that I would like to discuss is, but then, I mean, metaphysicians of science have always thought that atoms had exactly the same size, had exactly the same shape, because they were really pinning down the minimal, okay, the minimal kind of length, the minimum kind of volume, the minimum kind of size, okay? So how is it in this picture of loop quantum gravity? Okay, here we know that the shape of these chunks of space, these atoms, actually depends on the structure and how many links on the quantum number associated to the volume. So how we can endorse this picture? Then also a question that I have is really, what is the Rovelli's picture instead? I mean, he does not take these chunks of space as concrete entities, okay? So for him, a discreteness of space comes from the quantum space understood that, for instance, observables like area and volume had discrete spectrum, okay? So can the Rovelli picture instead actually enlighten the metaphysical debate with some new, fresh kind of interpretation of what models of space might be? So this is my conclusion. I hope that I'm running too much time. I'm sorry if so. Well, going back really to the metaphysics, what I'm not saying is that this is the right way to interpret loop quantum gravity. And I would like to discuss this with you in the Q&A answer, but this is not what I'm endorsing. But this kind of model can actually be carried to the metaphysical domain, can help us metaphysicians, okay? And what are the questions like, can this kind of model have more advantages, okay, than the normal actual discrete atomistic models what we normally have in mind? What are exactly the features that brings novelty to the metaphysical discussion, okay? So we know now that this kind of model does not bring the threat of being vulnerable to the WEYL argument, okay? Maybe can it gives us a new idea of how length should be calculated, okay? We can't calculate it on the number of atoms, so how from a metaphysical perspective? What about this length operator? Can give us a new insight of how we should calculate length. Also, it gives us the idea that, of course, the point in continuous space and the discrete view of space is not, they are not incompatible, okay? But they are recoverable, okay? So really here, I just would like to say thank you so much for listening to me and to listen what my project might be. And I'm also very thankful to all the people working in loop quantum gravity who came to my talk. And I really would like to hear what you think about this. Thanks.
So let's start with Carlo, please. Your microphone. Unmute your microphone, please.
Sorry. Is that okay?
Yeah.
So 3 very small comments and then a main point which you raised. The first comment is that I think that you did a great job. I mean, I think everything you said about loop quantum gravity, from my understanding, is correct. It's very good, and very clear and very clean. That's the first point. The second point is that indeed there is a lot of discussion about the length operator, but I think that in the context of what you're saying, everything you say about the length operator is okay, in my understanding. And in particular, the WEYL objection to discreteness, I just want to say that in the early days of loop quantum gravity, it bothered us a lot. We discussed a lot, I remember, because the very first models we used to try to rebuild Euclidean geometry suffer that problem. But then we convinced ourselves, and I mean the people I was working with, Liz Morning, by Ashiker and Pooling and And Daniele, I don't remember if you were already there at the time, you were a young student. But we convinced ourselves that...
I was in kindergarten.
Oh, you were in kindergarten. That's right. But you were precocious, so we convinced ourselves that it's solvable. I mean, I don't want to go into technicalities, neither about the length operator nor about the WEYL thing, but we convinced ourselves, no, I mean, that's not a problem anymore. If you do things properly, and as Daniele was saying, if you keep the fact that there's approximation involved, then you definitely can recover the Euclidean geometry. And the third little comment before going to the main point is you quoted Christian Wutwig for adjacency between points which are not adjacent. I think Christian is here, I believe, so he may comment, but I think he was referring to Lee Smalling that has tried to do some physics out of that and use that. But I don't think this is really a difference between the classical limit, because when you have two nodes which are with a link connected, which are far away, well, they are adjacent. They just represent a geometry which also exists in the classical theory. In classical GR, you can have very funny geometries in which you have tubes connecting different points. So that has to do with the strangeness of the space-time in classical GR. So I don't think those things are not there if the state represent in the configurations that represent Euclidean space. Okay, so this is just side remarks. Now let me come to the main point. The main point that you raised is, and you mentioned my complaining at some point against a strict sort of metaphysical, and I talk about metaphysics here, identification of this quanta of space with entities in a strict substantivalist perspective. Now, why did I say so? And what is the point? The point, and what's the relation with Vassallo and company? The point is that in quantum gravity, you're dealing with a conceptual complication of relativity, with a conceptual complication of discreteness, but also with a conceptual complication of quantum mechanics, right? So the point is quantum mechanics. And whatever you do, metaphysics, including input from quantum gravity, you're implicitly taking a position with respect to the metaphysical questions opened by quantum mechanics. Where you have exactly the same thing. I mean, in a Schrödinger particle has a position, is an entity with a position. Is this position to be taken as part of the ontology? Or is a position just a way some Schrödinger wave function interact with me when I hit the screen? Okay, so this is a hugely debated thing, and I don't want to give it say this is the right way of thinking, this is the wrong way of thinking. I mean, this is there are different options about how to place the metaphysical questions about quantum mechanics. Now, what Vassallo does, and his collaborators, is to take a Bohmian perspective. In a Bohmian perspective, there is a clean metaphysics. I mean, one might dislike Bohm for other reasons, or think that is useless or whatever, but the metaphysics is clean, and I think it's very good that there is a way of viewing quantum mechanics with a completely clean, in particular the way he does, in which the Bohmian way of viewing a particle is that there is a particle always somewhere at some point. So you break some of the, people would say, invariances of quantum mechanics, but that's fine. I mean, you take this particle and you have a clean metaphysics, and then the wave tells you how this moves, but this is part of the sort of the dynamical laws or whatever. Now, if you do that, which I usually don't do in my talk about quantum, because I don't adhere to, I think that there are perhaps other ways. But if you do that, then for a particle, you say, well, my metaphysical interpretation to quantum mechanics is that there is a particle always at every point, and it just moved around by the guiding equation of Bohm. Now, if you take that and you use in loop quantum gravity, which you can, it's completely legitimate, I think. I mean, one might resist and say, no, wait a minute. I want to be more covariant. I believe in relational quantum mechanics. I believe in many worlds. I believe in physical collapse, in other interpretation of quantum mechanics. But if you want to take quantum mechanics in that sense, then you have to identify the variables that are like the position of the particle, the variables that always are fixed. And the obvious way of doing in loop quantum gravity is indeed to say that these are the quanta of space of the spin networks. And there are never superpositions in the sense that superposition is it's in the wave. The particle is in a point in Bohm. So you always are, so to say, in a given spin network. And then you can have a completely substantivalist, metaphysical assumptions that the entities that represent space are discrete, circumvent the WEYL objection, and this is a picture given by loop quantum gravity. Whether it's correct or not, experiments will tell us. So that's how I think the option is. Of course, there's another option which say, well, I don't like Bohm. I want to give a different interpretation of quantum mechanics. Quantum mechanics tell me how systems interact, not where the particle is. The particle is not somewhere. It's just quantum spread. And then this is what I meant. Since I prefer this other way of viewing quantum mechanics, this is what I meant. Say, well, wait a minute. Don't take these things too seriously. In the sense that don't take a quantum particle too seriously. Schrödinger itself at some point said, well, we shouldn't think about a quantum particle as an object. We should just something that manifests itself. So that's my answer. So, I'm perfectly with you. There isn't any, everything you said I would subscribe. This is how I would use the alternative.
Yeah, thank you, Carlo. So also from your side, so this warning of not interpreting chunks of space as concrete entities comes from a metaphysical perspective. So from how you interpret non-relativistic quantum mechanics, and so you want to carry this picture also in loop quantum gravity. Okay, but correct. For you, it doesn't. It's not that like the Bohmian perspective is wrong, because also within loop quantum gravity, you can still interpret these chunks of space as as concrete entities. Yeah,
correct. I don't think that any of the main discussed interpretation of quantum mechanics are wrong. They're all right. Any world is right. Bohm is right. Physical collapse, we don't know, because that's a different story. It's decidable empirically. It's just which one do we think is going to be more useful?
Yeah. Also, may I ask?
Sorry, can I just make one comment on this? I agree with everything here, but I would suggest that if one really wants to develop a Bohmian interpretation of loop quantum gravity, it will not be enough just to state what the ontology is and how we should interpret the quanta of space that are described by the theory. Because Bohmian mechanics requires that you really write down an additional equation and modifies the whole story. So it's a bit more than just saying, okay, I take a certain viewpoint on the quanta of space identified by loop quantum gravity, for which, of course, there are many viewpoints you can take. You can try to interpret things according to different perspectives. But Bohmian mechanics will require more than that. It's not consistent, even in a non-relativistic case. If you just say, okay, no, particles are well defined in their position, and that's it. You cannot just do that.
You're right. That's what we have done in the paper. Acknowledge exactly this point. We have to, let's say, supplement the dynamics with this guiding the question.
So probably this is also why I wanted to call it like the primitive ontology approach rather than Bohmian, because, well, also like I'm not very sure that you have to. You must, or in any case, you're really forced to endorse this realistic view of chunks. If you're Bohmian, for instance, I mean, you can be Bohmian but still have an absolute space which consists of points, for instance, and then your particles are really the only material entities you have. But if you have a theory only of space and you're a primitive ontologist, then probably you are looking for the building blocks of space. And so this is why you want to divide your space in atoms. Yeah. So sorry, another, just to address Carlos' comments. So you said that you actually were worried about the WEYL's argument when you developed loop quantum gravity. So I read, but I'm not sure, that when first you worked on loop quantum gravity, you didn't know that you would have ended up with a discrete view of space. And that, so if it's true, is this related? I mean, at a certain point, the very beginning, were you thinking that you could retain the continuous view of space?
No, the discussion I'm referring to is in the middle of the 90s. So in the late 80s, we came out with the loop space and the first papers on loop quantum gravity. And then in the middle of the 90s, so a few years later, we started to try to write the quantum state that approximates to flat space-time. And we were thinking, in fact, this is relevant to what you're saying, we were thinking of writing a sort of mesh and then taking it in the limit in which is infinitely thin.
I see.
And the limit did not work. In fact, it came out of the equations. In the limit, it was something very strange was happening. So somehow, when you were trying to make the discreteness, the graph, so to more and more fine, it turned out that the mathematics was telling us that the distances were still Planckian. It wouldn't become smaller.
I see. Yeah.
So we got very confused at that point, and we realized that the mathematics is telling us that no, that's it. You cannot. That's the smallest you can do. And at that point, we say, oh, fantastic. Then we just approximate with a cubic grid.
I see.
Of a Planckian size. And cubic grid is obviously wrong. I mean, we didn't know the WEYL wrote about that, but you just clash against it immediately. I mean, it's just, you don't get homogeneity if you have a crystal. You have special, and so, but then we realized that, but it doesn't need to be a crystal. We have the results for doing something which is like an amorphous material where there are no special directions. And then if you work out the details, you can circumvent.
Thank you, Carlo. Thanks.
Lorenzo has a question.
Yeah, something that Vera was talking about, the Bohmian interpretation, and also Carlo and Daniele were mentioning this. So I'm curious about the ontology of the Bohmian interpretation is explicitly non-local, because you need to have non-locality in the hidden variables in order to use Bohmian mechanics. How can you reconcile this with general relativity, where the causal structure must be? I mean, I really can't get my head around this. How can you use Bohmian mechanics to quantize general relativity if one is explicitly non-local?
Okay, so who is answering this question?
You can.
If the question is too difficult, don't worry. I mean,
that's an open question. That's an open question. But first of all,
you can.
Quantum mechanics is non-local by itself. It's not a problem.
No, I disagree with that.
Of Bohmian mechanics.
I totally disagree with that. Bohmian mechanics is certainly non-local. Quantum mechanics is not. I disagree.
I mean, non-locality is in the wave function. So
sure.
Both.
That's not quantum mechanics. That's not the ontology of quantum mechanics.
I mean, what Bell's theorem says is that quantum mechanics is non-local, no? The violation, the experimental violation of Bell's theorem.
Bell's theorem says that quantum mechanics is either non-local, or you have to relinquish counterfactual definiteness. So you have the choice. It's not necessarily non-local. You have this choice. And
what is
people like Bohr just say, okay, let's give up counterfactual definiteness and keep locality. So I mean, you can certainly keep locality in quantum mechanics. You cannot do that in Bohmian mechanics, but in quantum mechanics you can.
Can I put a thing here?
Sure.
in the way Antonio and Bohmian mechanics can be interpreted, and itself can be given different ontologies. So one way is to think that the ontology is attached to the particle and interpret the wave function as part of the dynamics. And then the dynamics is definitely non-local. So if you have two particles, what happened to one particle not only depends on the Schrödinger function, which has a local evolution, but also depend on where the other particle happened to be. So sort of use the other particle is here or here, this moves differently. Right. Okay, so it's definitely non-local. So it's non-local over and above whatever sense, much weaker sense, the violation of the Bohm inequality tell us that there is some sort of vague non-locality in quantum mechanics that you might not call non-locality if you want.
Yes.
Now, your question, if I understand correctly, Lorenzo, was how can this be coherent with generativity? Well, it can, of course, exactly the same way in which if you do the Bohmian theory of two particles, say colliding, jumping around, the quantum theory has this precisely no sort of non-locality. But if you do the classical limit, you don't see the interference anymore. You don't see the
right.
And in the classical limit, you get back to a local dynamics. So it's the same in what Antonio wants to do. I mean, and I see no reason for this not to work. In fact, there were a number of attempts to do Bohmian interpretation of quantum gravity, independent of loop quantum gravity, just with three-dimensional geometries. And that's what happens. I mean, you have a guiding equation, you have a dynamics of the geometry or the spin networks, which is no local in the sense that what happens here depends on what happens somewhere else. But in the classical limit, you don't see that anymore. So it's compatible with the classical limit. You might say, well, it's not compatible with the spirit of generativity. I agree. But that's true also for Bohmian, standard Bohmian. So that's one reason for which people don't like Bohmian. And many people don't like Bohmian. So one of the costs of Bohmian is that you have to believe that. If you don't like that, you have other options, each one having a cost.
Right. So basically you're saying that just like in normal quantum mechanics, you have this hidden variables, this censorship about the hidden variables that they are hidden, so you don't see. So the same thing can be done when you use Bohmian mechanics for general relativity. This is what you're saying. So,
yeah,
so then
yeah,
you can,
yeah.
Okay.
Yeah,
Thank you. Thank you very much.
Other questions? I don't see hands raised. So I can ask a question, which is about the metaphysics of laws of nature. Imagine that this ontology we got of atoms of space is just right. Do you see any take on the laws of nature which is, let's say, strengthened by this kind of ontology? For example, if I am a dispositionalist with respect of laws of nature, does this discreteness of space help me? Or if I am a humanist, I'm just, let's say, I find more problems. Do you see that there is some sort of discrimination that this ontology has with this respect?
Yeah, well, this is a difficult question. For now, I don't see much problem so for the metaphysics of laws. I mean, I would have to think about it more careful. I guess that, I mean, the problem is really because since now we are really talking about the kinematical part of you know, the theory, and also I was not talking about the interaction between the matters and the space. And so I really do not know how this would turn out to be. I mean, I know that Carlo developed the covariant loop quantum gravity, which utilizes spin forms, and you know, and that he could really come up with also dynamical theory for loop quantum gravity. But since I'm not familiar, then I'm not exactly sure how this might play in a dynamical setting. And so I don't know how it would be for really dynamical laws of nature. But yeah, this is definitely an interesting question. I mean, what I can see is that probably a Humean, regardless of really whether the laws of nature play any role here, would be very probably happy to have your view, because of course you have this very discrete view of space with the physical entities. Of course, a kind of like more intransigent or fundamentalist Humean would say, oh, but you know, my space needs to be point-like, okay? But probably, I mean, between an ontology with superposition and weave states that, you know, are superpositional states, and then an ontology with clear building blocks in the fundamental structure, even though they're not point-like, probably they would choose the later. Yeah. Also, what is really interesting for me, and then, yeah, sorry, it's really what do these quantum numbers mean? That, you know, these quantum numbers that we attach to the nodes and the links, what kind of properties we can think of. And I think that in the dynamical theory, we can be we can really see what these quantum numbers, what is their role. I mean, do they represent dispositional properties or just categorical properties, or yeah.
Okay, thank you. Other questions or comments?
Just
Daniele,
a comment, sorry. Maybe you can all explain the issue better to me. So I can see how the view you take, you may take on laws of nature will affect your interpretations of quantum mechanics, for example. In particular, I don't know, changing your view on the role of probabilities and what they are supposed to be. But the whole point about the atoms of space having to do with the ontology, to me seems to be about what are the physical systems your theory is about. And I don't see how a choice of the physical systems you're trying to write laws of nature for will really change, can really affect how you view the laws of nature themselves. So I'm not really sure. So I don't have any suggestion for how the laws of nature, the view of laws of nature will be affected, but I really don't see what the logical link would be. So I decided that I'm interested in in a certain physical system. So I want to write down laws of nature for it. I have my views on what laws of nature could be, and I don't really see how that will be changed or will be affected in which aspect by deciding that among the physical objects in the world, that they are in fact the constituents of space.
I think, well, maybe this question was for Antonio, but maybe I will say something. Yeah, well, what I think is that some kinds of interpretation, ontological interpretation, metaphysical interpretation of your physical system might push you to endorse a particular kind of metaphysics of law. So for instance, Bohmian mechanics, since we have been discussing that, well, what are the so-called properties in Bohmian mechanics? Okay, so for instance, if you think that particles have, I don't know, that positions are dispositional properties in Bohmian mechanics, then you might want to, I don't know, endorse a dispositionalist or structuralist, I don't know, view of laws of nature, because it might fit better with, you know, your general conception of, you know, the system. But yes, I do not think that changing physical state, a physical system, induces you to change your metaphysical views of nature, except for the problem of probability that it's different.
Exactly. So, but that's where my doubt was coming, my confusion was coming from. So, of course, when I say that the world is made of such and such physical systems with such and such property, I have to be a bit more precise about what it means for a system to have properties, and then I can go for disposition, and that affects also how I see laws. That I agree.
Mm-hmm.
What is unclear to me is why my view on laws should be affected by the very addition to the set of physical systems.
Yeah, no, I don't think
of space so. Per se. I mean, regardless of how I interpret what they are and their properties and so on.
Yeah, well, I don't know. For instance, Humeans. Oh, sorry, Anton. Anyway, for instance, Humeans. I mean, they say, well, I mean, laws of nature are really part of the best system that describes the motions, or in any case, the development of my mosaic, which is point like. So they have, I mean, in their laws of nature, they take so much metaphysical views about what the mosaic is and about. So maybe that might.
Okay, so the logic is if in your view about laws of nature, and maybe in the very definition of the laws of nature, you are bringing in space-time, first of all.
Yeah,
and
exactly.
You're bringing in particular a view of space-time which is continuous, and so it doesn't admit the notion of constituent or atom of space. Okay, then of course your law of nature will be, the view of laws will be affected.
But I think it will be very artificial anyway. So I kind of agree with you. Oh yeah, sorry. Vince.
Carlo wants to say something. Carlo? Unmute yourself.
It's another question. It's another question. I don't know if we're done with that.
So Vincent was following up on this.
Daniela, what you're saying is correct, but it's maybe just slightly different in the case of your physical systems you're considering are space and time themselves, because the standard views on laws of nature make certain assumptions about space and time. Take the Humean view or dispositions or primitive approach to laws of nature. For instance, assume certain assumptions about temporal evolution, these kind of things. And of course, if your laws of nature are about space and time themselves, then you might have consequences depending on the kind of views you have on space and time. So this might have an impact then on your conception of laws of nature.
Okay, so again, the general answer to my doubt is that to the extent in which, in your view of laws, you are making assumptions about space and time, then of course, whatever you new or strange you say about space and time in your theory of quantum gravity is going to affect it. Okay, I understand.
Yes, exactly. Certain views about laws of nature, for instance, exclude explicitly closed timelike curves, because they would be incompatible with the existence of closed timelike curves, or certain dynamical structure of space-time, certain weird topologies, these kind of things. So they would be incompatible with these strange space-time. So you can imagine in the case of quantum gravity, maybe not all conceptions of laws of nature would be easily, or you have to do some work.
Okay, but then my bet, make it public, would be that 90% of those will be already challenged severely by general relativity, even before going to fancy quantum gravity approaches.
Yes.
Carlo wanted to add something.
Yeah. Let me endorse what Daniela just said. I bet with him. Now, since we are enlarging.
Sorry, Carlo, I'm not going to share the profit of the.
Okay, it's an independent bet. Since we're enlarging a little bit, Vera, I would like to ask two questions to you and know what you think about two things which are related. One very simply is that, I mean, while you were talking at some point, Daniela had a sort of reaction, an anti-metaphysical reaction, a typical physicist anti-metaphysical reaction. I'm reading Ladiman right now, an old book in which he goes on and on against the uselessness of metaphysics. And I want to know what you think about that. And the second question, let me formulate together because they're related. At the very beginning, you started by saying, if I want to be a substantivalist, I think that there is space and then the rest. And I sort of picked in and say, well, wait a minute, well, what do you mean? And the rest is, my view about substantivalism as an alternative to sort of relationalism about space-time is that it's an empty discussion, because it's just a terminological issue which has really no substance into it. Namely, Einstein has made a discovery, a serious discovery, namely that Newtonian space and Newtonian time are the gravitational field. And so to me, this means that metaphysically, ontologically, they are exactly on the same ground as the electromagnetic field, which in turn is the same ground of the Dirac field. So the discovery of the discreteness of the quantum space is a little bit like discovery that there are particles, because the Dirac field is quantized. So electrons are the same thing as the quantum space. That's my own take about that. Mm-hmm. Now, there's nothing wrong, of course, in taking some of these quanta entities, which are the quantum space, and they do have special properties that electrons don't have. Definitely. So they may very well deserve a special name, and let's call them space. And then suddenly I am a substantivalist. But the strong opposition between space as a container and whether it's discrete or continuous and matter in it is so much weakened, seems to me, by generativity, as Daniele was saying, and therefore by quantum gravity, which then I asked myself, is it worthwhile insisting in this, in holding this this strong distinction? And once again, the drive is somehow, remember that I'm reading Lediman. I understand trying to attach, to do metaphysics using modern physics, but shouldn't we just be guided by it without trying to superimpose intuitions which come, after all, from a limited experience we have? This, you know what I'm talking about. I just want to not argue for anything. I just want to know you reacted to Daniele by saying, "Oh, I would have a lot of things to say about that." Well, I want to hear what kind of things you have to say.
Yeah, thank you, Carlo, for bringing this up again. So, of course, I'm always a bit skeptical when metaphysicians of science try to justify an interpretation of the ontology of a theory in the name of some metaphysical presuppositions of how the world should like. So in this case, for instance, I'm a very skeptic about the primitive ontology approach. However, I have to say that if we really stay away from any metaphysical presuppositions, then physics, I think, cannot tell us what exists in the world. So in any case, I think that even physicists, when they have a narrative about what their theory is and about, what the world is, then they implicitly, I think, have or uses some metaphysical presuppositions of what the theory is telling us. Then, of course, so for instance, like you were discussing before about like fields, right? Like the electric field. So if you read, I mean, I'm sure you did, but I mean, if one reads Faraday and Maxwell when they discovered the electromagnetic field and lines of forces or this kind of thing, then I mean, Faraday maybe didn't have already such an articulated ontological view. He was saying lines of forces everywhere, but he had this very strong imagination of what these lines of force should be. And then with Maxwell, right, this. So even when I read a physicist writing, I see so much ontological thing going on, and the electromagnetic field, and so the discussion of whether it was really a physical entity or whether it was not a physical entity but could be reduced to properties of particles, charged to particles. It's really paradigmatic for me to see that even physicists, there were no philosophers, I mean, at that time really saying, oh, you should believe that physical space did not exist. But even physicists were saying, come on, how can I attribute a physical reality to this empty space that I don't see, I don't touch, only because this magnet moves around when I put this charged particle around. So I think that the metaphysician here can have a role, because it says, well, look, what are you presupposing? Why are you presupposing this? And tries to make things clearer. Then going to the second question, which is related. So the metaphysician has exactly this role of trying to think, trying to make your metaphysical reading, metaphysical presupposition clear. And sometimes I agree, we exceed into too much, I don't know, trying to be more and more precise. So for instance, the electromagnetic field. So I don't know, like philosophers of science, metaphysicians of science are really debating, oh, should we, is the electromagnetic field just a collection of properties of space, or it's this kind of physical entity that evolves in space? And even like, I don't know, wave function realist in quantum mechanics. Oh, so we go into the configuration space where this field, the wave function lives. But what are these complex numbers, you know? I mean, so should we think of the wave function just a collection of these complex numbers in a space? Or actually, no, it's a physical entity that, you know, evolves. And, you know, this kind of metaphysical questions, in the end, they do not really amount to a great difference. Or in any case, sometimes even not a meaningful difference, I think. So the balance, I think, has to be really gauged here, and it's very difficult. I never thought that this relationalist, substantivalist debate can also be seen as maybe like a fictitious or artificial kind of debate. But maybe it is, you know. So yeah, I need to think about this. And in any case, I'm sorry, because in the very beginning, I give you a very kind of simplistic toy model of what substantivalism is. So you can even be super substantivalist and, you know, think that even physical objects have the same intrinsic nature of space, and so they are just, you know, with the further property, but it's just chunks of space. So you have very different views within the substantivalist. And even like this picture of the container, but I mean, substantivalists can regard the space as even kind of like fluid that permeates all things. But then, as you said, I mean, does this really matter overall? Is this distinction meaningful? Can a physicist really come up with an answer?
Yeah.
So, sorry, the very last point. So, for instance, in this debate between the primitivist approach that sees the chunks of space and concrete entities, and your kind of view, yeah, I mean, the standard view of low quantum gravity, but it's endorsed by you, that we are just talking about discreteness of the spectrum of this area and observable operators. I mean, my question is, can we ground this discussion on more physical level rather than metaphysical? Is there anything in a loop quantum gravity that pushes us to endorse one interpretation rather than the other? And these are the questions that, you know, fascinates me.
Yeah, I think I'm with you. You put it very, very wisely. I think it's a matter of balance. It's a subtle matter of balance. And if I think of myself, I mean, definitely, sometimes I argue strongly with my physicist friends on the relevance of metaphysical questions. I mean, you mentioned Faraday. There is a chapter in his book, the thing is whatever about electricity, in which he says, and now I go to the deep question, are these things real, the Faraday lines? And I think it's one of the greatest points in the history of science. I mean, he's really creating the notion of fields on which modern field theory developed with a clarity which is probably even not mathematical, of course. I mean, he was a disaster in mathematics, but physical, even more than Maxwell, who were not thinking this way. So yes, and on the other hand, I also have the opposite reaction to too subtle metaphysical questioning by philosophy, exactly in which you said. So I'm very much with you about relational versus substantivalist interpretation of space-time. I have argued that it's the question is really dissolved in classical GR, not in quantum GR. In my old book in quantum mechanics, I have a little chapter on that in which I just argue that if you, at the light of GR, if you look closely at what one side or the other side says, it's the same thing. It's just an issue of names. That's my and related to that, and related to, I just want to raise a point. The substantialist view of space as an entity which is there. Okay, take away matter, forget fields, take away matter, there is still space there. My understanding, and I want to bring history of physics, is that it's really an invention of Newton. Is not intuitive, is not our basic natural intuition. If you read Descartes, if you read Aristotle, if you read anybody else, except Democritus, except the Epicureans, which have this notion of void, which is a pre-running of Newtonian space, the understanding of space pre-Newtonian in the Western culture and the intuitive understanding of space is completely relational. Where am I? I am in Canada. It's the things around me that determines where I am. Where is the wood? Where is the trees in the forest? So where is about location relative to other things. Euclidean geometry, if you read Euclid, is not about space. It's about objects idealized. It's a shape of idealized objects. So I say that because the intuitions we have not only might be wrong, as we all know, and not only are variable, but are strangely historically determined. And sometimes we consider completely intuitive something which is a science of 3 centuries ago, which we have interjected so much that now we have to think this world this way. This doesn't, I don't want to, I'm not letting, I don't want to take away the interest of the work of modern metaphysics. I mean, sometimes I get bored by it. I say, oh, come on, guys. I mean, you're just like medieval scholastic dancing on definitions. Sometimes I think that it definitely can be good also for physicists to think about these things.
Okay,
yeah,
thank you. Nils Martens asks Carlo to provide a reference to his book chapter where you...
Oh, it's my, the book is Quantum Gravity.
Mm-hmm.
And I'll put in the...
So it's your manual. If it's in the manual, I put the reference already.
Yeah, it's a manual. It's the old one. It's not the one with...
I put the reference.
And there is a, I think if you're reading the table of matter, there is a little...
it's the one in 2004.
Chapter, which is relational and substantivalism.
Yeah. Yeah. So, yeah. So it's here. It's Cambridge University Press. Yeah.
Last question for today, Daniele.
Yes, I have hopefully 3 very brief comments about the discussion so far, both what Carlo and Vera have said. So one very brief about substantivalism and relationalism. I agree with what Carlo said, and my advice to the metaphysicians who are trying to debate the issue, if they want to make sure they are debating the issue in light of general relativity, just try to make sure that when you define your terms and you try to clear up your view, you do not have the manifold in mind for space. Make sure you're not trying to debate what is the role of the manifold itself, whether it is a substance and the points in the manifold are substances or relations, because that's simply what GR sort of tells us. It's not really physical. Try to translate whatever you're trying to say in terms of, indeed, the gravitational fields, the other matter fields, the electromagnetic fields, and their relations. Then you can indeed, I agree that the issue is sort of a matter of definitions. It basically depends on where you put the gravitational field. If you can leave it there, treat it as a substance and try to define everything with respect to that. Or you put it together with the matter fields and you say, well, it's a physical object like the others, and so everything is relations. There is some leeway there, but just make sure you're not trying to give a meaning to the manifold, because GR will give you trouble if you try to do that. Anyway, that's the comment. And the other 2 comments are more about the metaphysics physics relation. Indeed, I was a bit, how to say, reacting to that, hopefully not just because I'm a physicist. My point was, the points I had in mind is the following. So I was reacting not to the statement or to the view that metaphysics is crucial and very important in developing and also in understanding physical theories. Quite the contrary, I would be a strong advocate of that unless you become scholastic, indeed. But there are 2 points. First of all, I would argue that you have to use and develop them together. So what I was reacting against is the methodological view that you choose your metaphysics, you decide that on intrinsic arguments, that's the best one, and then you try to fit the physics in it, and you reject or modify any physics that doesn't fit. I think the 2 processes of mutual adjustments have to really be worked out in parallel. Of course, you can modify the physics because it doesn't fit some metaphysics, but it should work also the other way around in parallel, that you're ready and very actively doing so, modifying your metaphysics while you are trying to understand what the best physics is. So that's the first point. With the word of caution, and then I close, which is that just like physical theories are severely underdetermined by data and experiments, then whatever metaphysics you try to develop is going to be severely underdetermined by the physical theory. So you could have different metaphysical viewpoints even for given theory. So there is some room there, and it's not a bug, it's a fact.
Yeah, I totally agree. Yeah.